All right, so next up is Jake Huryn from OSU, who will say some more about rigid local systems.
Thank you, Stefan, and thank you all for being here bright and early this morning. Yeah, so I'm going to say a bit more about rigid local systems. We already started to see some things about these, but go into more detail. And hopefully by the end of the talk, I'll convince all of you that these are really interesting from a geometric viewpoint, and also they provide a really good example of local systems which kind of sit at really the intersection of all of the complex geometric stuff that we've been seeing, and also the arithmetic side as well. So let me get started by giving some definitions here. Let me first describe the setting that I'll work in. So X is going to be smooth connected, quasi-projective variety over C, and gamma will be a topological fundamental group of the associated complex manifold. I'll be ignoring base points throughout the talk. Hopefully doesn't cause any confusion, but I think it might be more confusing to try to keep track of that. So X bar is going to be a smooth compactification. And we want a bit more than this. So it should be a good compactification in the sense that the boundary divisor has normal crossings. So such compactifications exist by resolution of singularities arguments. And let me, for notation, decompose this into its irreducible components. The di's. And there's one more thing that I need to say, which is I'll use TI for the local monodromy operators. So TI is supposed to be a loop around DI. So in quotes, but for completeness, let me sort of say in more detail what exactly this involves. So we want to fix some open ball in this compactification and maybe avoid any singular part of the divisor. So everything works out nicely. Then TI should be a generator. Well, the image of the fundamental group of the punctured ball. So this delta I minus this divisor component, gamma. Of course, some choices involved in defining such a map like this. But this guy here is just easy to see topologically. This is Z, so we can pick out a generator TI of the image. And of course, there's a lot of choices, but maybe the upshot here is that TI or TI inverse is well defined up to conscious, which is all we'll kind of need in this setting. So that's sort of the setup that will be kind of enforced throughout the talk, more or less. And it's in this setting in which we can sort of define rigid local systems. So let me maybe first say in words without writing anything down that a rigid local system is supposed to be, a local system on this complex manifold in the sense that we've been discussing this whole time, which can't be deformed. And in order to make this a good definition, a sort of non-trivial definition, there's sort of some data that this deformation would have to fix. For example, the determinant of the local system and the local monodromy. So these would be the conjugacy classes of these monodromy operators in your local system. So can't be deformed while leaving those two pieces of data fixed. So that's the idea to have in mind, and what I want to do now is give a formal definition of this. So these will be define these representation varieties. In order to give a formal definition. So fix some data here for these definitions. So R is always going to be the rank of these local systems. So field K, theta is going to play the role of a determinant. Some homomorphism like so. And conjugacy classes, so C1, Cn, so these conjugacy classes are monodromy. And to make this definition, I guess should probably view these conjugacy classes as locally closed subschemes of this affine algebraic group. But at the end of the day, for Simpson's conjecture stuff, it's not really necessary to do that. But, okay. So to get these representation varieties, define some functors. So rep gamma R to set. We'll take a ring, spin out toms from gamma to GL R. And this is a finite type affine scheme over Z. And the principle behind this was explained already by Daniel. So this gamma is a finitely generated group because our topological manifold by some classic topology facts is homotopic to a finite CW complex, say. So that guarantees its topological fundamental group is finitely generated. And then what this functor is doing is it's just associating to every ring tuples of matrices corresponding to the generators, satisfying all the relations. So it's just some closed subscheme of GLR to some power cut out by some equations. So let me just say this is a finite type over Z. So kind of a nice thing. I guess what will be more relevant for us is the sort of refined version of this functor. We write rep gamma R, theta C. So this one will be valued in rings over our field K to set, and okay, this one takes a bit more to say here. So it's going to be a subfunctor of that guy over there. So first of all, okay, we have our fixed determinant, and I want to say we have fixed conjugacy classes. So the way to say this, so for all I, and for all maps from our ring to a field, the local monodromy lives in this conjugacy class. Okay, that's this refined version, and yeah, the formulation here is a little bit cumbersome. on the level of functors of points just because these CIs are something locally closed, not closed in general. But just want to think about this fixed determinant theta and conjugacy classes of local monodromy, the CIs. Okay. I'm sorry? Yes, that should not be rho. Thank you. Okay. So, having made this definition, I can give a formal definition of a rigid local system. So one of these is rigid. Okay, and that one, I guess a K point here is rigid if its GLRK orbit is a connected component. Okay, so what's going on? So here GLR is acting on this representation variety by conjugation, right? Conjugation preserves all this data that we've wanted to fix. And so we ask that the GLA, that the orbit of this rho gives us a whole connected component. Sort of another way that you can think about this. So this orbit here is nothing more than the image of some which on the level of functors of points is given just by conjugation. And yeah, so that's what a rigid local system is in this setup, and hopefully it's kind of is pretty reasonable. You know, this representation, we can deform it to anything in its connected component, and we want to say that when we do this deformation, we don't get a different representation, we get something conjugate, or something in the same GLR orbit. Yeah, I guess like a set theoretic image, but you can do this on the level of geometric points, and that's good enough. Maybe easier to think about. Yeah, other questions? Yeah.
What is CIF of F?
CIF. So these are the F points of this locally closed subscheme of GLR. They're just the I guess the F valued matrices which live in this conjugacy class. I mean, that's what it will be. Yeah.
Is there any reason why we require this role of TI validating is in CIF instead of just CIR?
Yeah, I mean, so it's just sort of a feature that these CIs are like locally closed rather than closed in general. So sort of want to say this in order to get it to work out correctly.
So otherwise, we do not get representable functors.
Yeah, I mean, I didn't think about whether it's representable or not, but sort of the functor of points of like an open subscheme is like the things whose image does not land in the complement, and that's what this is trying to say. But yeah, it's not super important here. So and maybe I want to say here something like it's rigid for some compactification. A priori, this notion could depend on the compactification, and I maybe won't say I don't really know anything about the independence of compactification, but it's rigid if this happens for some compactification here. Let me make some remarks. So I guess to tie this back to in the talks with these moduli spaces. So these really aren't good moduli spaces because you would want things to be up to isomorphism. So to get moduli spaces, so we would want a quotient in some appropriate sense by GLRK action. So you can either do like a stack quotient or a GIT quotient, or you do the stack of invariant functions on the representation variety. And this, for example, will give you a force moduli scheme. So these are just ways to get a true moduli space rather than just one of these representation varieties. And from this perspective, rigid just means being an isolated point of the moduli space, the appropriate moduli space. So maybe a simpler definition if you use these less naive moduli spaces. And okay, so from this perspective, this definition has an obvious counterpart. So a local system is cohomologically rigid if it's not just an isolated point, but a smooth isolated point. A reduced isolated point of the moduli space, so it has no infinitesimal deformations. So maybe I'll say sort of why this is called cohomologically rigid. This comes down to so the Zariski tangent space. If you want to compute the Zariski tangent space of this moduli space, our representation, something like this. So being cohomologically rigid is saying that this kernel is trivial. So that's a cohomological reformulation of this notion. And I'll have a little bit more to say at the end about cohomologically rigid things, but
maybe rho is irreducible. We want this to be, otherwise, I guess, is it in the course space or the stack?
yeah. So I guess take the stack. Take the stack. Other questions? Yes.
Gamma is pi 1 of x, not x bar, right?
Pi 1 x. Yes.
So why does the definition of rigid depend on the compactification?
Well, because of this local monodromy, defining these TIs operators dependent on the choice of compactification. Okay, so I guess that's the generalities in terms of defining rigid local systems in this setting. And so maybe now I will move on to Simpson's conjecture and say why we might be interested in rigid local systems. Conjecture. So I guess maybe this isn't exactly how Simpson formulated his conjecture, especially because he was talking about only projective x. But let me get the following formulation. So I'll start with an irreducible system. manifold, and okay, so irreducible rigid local system. Sorry. And I want to assume two more things about this one here. So first of all, it has finite order determinant. So this, and second of all, it has quasi-unipotent local monodromies. So let me say there exists H, positive integer such that all of these local monodromies to the H power unipotent. Okay. So we have these two conditions, and then where I would call this from geometry in the sense that we've been talking about before, namely there's some Zariski open of X where the restriction of rho appears as a direct factor of cohomology of a family over that Zariski open. So let me not write that down, but that was our notion here. Okay, so first of all, I mean, we've already said several conjectures about, given a local system, some conditions imply it comes from geometry, or maybe if and only if it comes from geometry. So this is something along those lines, and we'll see the relation to those conjectures in a second. But first, so if rho, let's say we start with something coming from geometry, then these conditions 1 and 2 will hold, so they're reasonable assumptions to make. So the second one is this quasi-unipotent monodromy, theorem which we saw in the curve case in Gleb's talk. And this first one is a consequence of some result in Billions Hodge 2 paper. And okay, that's, I guess, maybe the only remark I wanted to make here. So this is one way to state Simpson's conjecture. Not a terribly controversial formulation, I hope. So I guess kind of the remainder of the talk, in some sense, will be about evidence for Simpson's conjecture. So let me give an overview here. So Simpson proves some things related to this. So first of all, so at least the statement that I saw in his paper is for X projective, but maybe somebody has done it in more generality. So, but in this case, rho is a direct factor of a rational variation of Hodge structures.
So without particularly this is in terms of coverage.
Okay, great, yeah. Great. So we have this result, and okay, this is to be compared with the non-abelian Hodge conjecture that we saw yesterday, which was saying, okay, if your thing is underlying as DVHS, then it comes from geometry. So it's sort of a very similar kind of result. So another result due to Simpson, again in the projective case, and then takes a bit more work to extend it. Is that this local system rho will be arithmetic in the sense that Sasha introduced. And then, okay, of course, we want to think about this relative Fontaine-Mazur conjecture that we were told, which was that any arithmetic representation should come from geometry. So really this Simpson's conjecture about rigid local systems is kind of somehow in the intersection of these two conjectures that we saw. So I think both of those were yesterday. So some other evidence. So maybe see more about this later today, but Eno and Gershenig proves that actually this rho is essentially integral. It's conjugate to a local system with OK coefficients. So K, number field. And this is, again, what you would expect for something coming from geometry, because you have cohomology with Z coefficients.
So this is like cohomology.
Yes, sorry, cohomology, yes, sorry. Thank you. So for rigid, maybe not quite known, but for cohomologically rigid. And this relies on very deep results. Laford's proof of the local Langlands for GLR over function field. So something very arithmetic going on here. So I guess our first look at rigid local systems was in the case of punctured P1. So in this case, it is known due to ket for x inside P1, open subvariety. And this relies on this whole machinery of middle convolution. And finally, let me maybe say one more, which is maybe a little bit of a cheating way of saying it, but to make it consistent. So a consequence of some deep theorems of Margulis is that it's true X is this moduli space of principally polarized abelian varieties with level M structure. So a consequence of some result which, well, it's kind of slightly silly to say it this way because this result kind of trivializes Simpson's conjecture for this X, but does prove it in this case. So the goal for the rest of the talk would be to explain some bits of two and five here, so arithmeticity and this Margulis stuff.
I'm sorry, so just to be clear, all this evidence is like if you have all the assumptions from Simpson's conjecture and you have some extra, like extra conjecture or something.
Yes. Yeah. So the row here is supposed to be as in Simpson's conjecture. Yeah. Yeah. Other questions?
Does Margulis result require GL?
Yeah. Sorry. Thank you. And I'll sort of say why. Thank you. Okay. So maybe now I'll start talking about the arithmeticity part. So try to prove that the rigid local system with finite order determinant and quasi-unipotent local monodromy is arithmetic. So approach the proof. So let's, maybe now, okay, I should say fixed row as in the conjecture. So with these properties. So R, so what we're going to do is sort of descend, spread everything out. So R will be a finitely generated subring of C such that everything spreads out. So all the same properties that we wanted. Things are smooth and X bar is projective, normal crossings, etc. So, yeah, I mean, I guess in order to the next thing to say is that in order to get some sort of arithmeticity statement, well, we're starting with a complex rigid local system. So we want to have coefficients amenable to arithmetic, so that's what I'll say next. So how can we do this? So the representation variety whatever. This will be defined over QR, just need sufficiently many roots of unity to make it defined. Although you can sort of work with a different variety defined over Z if you like, where you just consider all representations satisfying 1 and 2, and that will be a sort of simpler thing, if you like. So rigidity, okay, tells us that this rho gives us a connected component under the GLR K action of this variety defined over Q bar. So that connected component will have some Q bar point. So rigidity implies that rho is conjugate to representation Q bar. Let's just say we replace rho by this conjugate, no harm in doing this. And then we'll factor through by the finite generation of gamma, something like OK equal to n. So K a number. Okay, so already this is like almost this integrality statement 3 here, except there's this n. And it's a lot of work to get rid of just that n to get this integrality. So we get something like this, and let me fix now place of k, place of k, not dividing n. Then we have, so we can map into here and then further complete here. And finally, okay, now we're in business. So this target here is a finite group as we've seen before, so we can get étale local systems finally. So this homomorphism to a profinite group, further factor through the profinite completion, which by this Riemann's existence theorem is the étale fundamental group. So let me omit the étale of X, and then we have these comparison theorems for base change, algebraically closed base change. So we can, oh, sorry, okay, K. Let's just say this is frac. Okay, so some finitely generated field over Q. So we have something like this, mapping to GLR. And let me just say K lambda here for simplicity. So let me call this rho sub lambda. And now it's something genuinely étale. So in this setting, phrase a theorem. That this will extend to, well, maybe admitting some finite extension of our K. Something like this. So K lambda bar coefficients. Rho extends to this for some finite K, and this was sort of the arithmeticity property that Sasha introduced, descending to the thing over a finitely generated field. So how are we going to get at this? I guess first I'll say, yeah, I'll only describe the proof in the projective case. So that we don't have any local monodromy to worry about, which will sort of complicate the picture a little bit. And if you're curious about what to do in the non-projective case, you can ask me. Okay. So after making some enlargement of K, we'll pick up a rational point. And so this will split our homotopy exact sequence, enable us to use this Galois action that was previously discussed. So then so split. Let's just fix a rational point and a splitting of this guy. So we want to act as follows. So given a Galois element, let me say rho lambda acted on by sigma, this will again go from here to here, where we conjugate on the inside. So we get a Galois action on these representations, and we want to use this. So the idea is going to be to use rigidity to say that this rho lambda is more or less stable under this action, and then that will allow us to descend to K, from K bar to this finite extension, K lambda. So to maybe phrase this another way, so we get a map from the Galois group to our representation variety with K lambda points given by sigma maps to rho lambda acted on by sigma restricted to the topological fundamental group gamma. And this will be continuous for this L-adic topology, or lambda-adic topology, simply by the continuity of this Galois action here. And now we can try to invoke rigidity. So what will rigidity say? Well, we have this continuous map. So there's some open neighborhood of the identity which is landing in the Zariski connected component of rho in this moduli space. So by enlarging K, we can assume the whole thing will land in this Zariski connected component. So enlarge K, I assume image is in the Zariski connected component rho, and now invoke rigidity. So hence, this rho lambda sigma will be conjugate. So let's say p sigma rho lambda, p sigma rho, p sigma inverse. So p sigma is bar. And okay, so this gamma is dense in the étale fundamental group, so this will extend to a conjugacy relation like this. And this is essentially sort of the sense in which this rho lambda is stable under the Galois action. So now we want to descend. So, okay. So I'll use this P sigma bar for the image of P sigma in PGL. And so the reason to do this here is that because of the irreducibility of rho, this implies that there's really just one possibility for what this P sigma bar could be. Schur's lemma is unique. So this will actually give us this will be a homomorphism by this uniqueness and in fact a continuous homomorphism to check continuity, but nothing there. And okay, this would be enough to build a PGL valued descent of our original rho lambda, but in order to get something GL valued, we want to lift this guy here. So the way we can do that is the following. So this map here, we have a surjection like this, and then the matrices, which are in the maximal ideal, congruent to +1. And this is going to map isomorphically onto whatever its image is. To see this, because well, the only scalar matrices in SLR have roots of unity, and these won't be congruent to 1 modulo the maximal ideal. We get this isomorphism here. So by, again, enlarging K, we can assume that all of these P sigma bars live in this open subgroup lambda. K, so P sigma bar lives in this open subgroup lambda for all sigma, and so we get this unique lift along the other side. So sigma maps to P sigma, so choosing some P sigma appropriately. Or the SLR doesn't. Continuous. Those will be our lift of these P sigmas, and now we can put these together to get our descent of rho lambda. Just erase this. So the claim is that after we've made all of these enlargements of K, okay, we can now take K lambda to be equal to this particular K. So how do we define our descent? Give it a name. Something in here looks like something in this K bar times the Galois element by our splitting. I want to map it to rho lambda gamma times P sigma. And this will be a continuous homomorphism. Yeah, I have to check that it's a homomorphism, but this will have the structure of the semi-direct product of this geometric fundamental group and the Galois group. So it will just be right back. So here. Okay. So that will give us the descent. Are there any questions about that? Yes.
So is the point where you need to use the K bar lambda at is like choosing the capital P's?
Yeah. So actually, I mean, I think just like extending this argument a little bit, you can get rid of the bar. When a priori these p sigmas are living in k lambda bar.
Is it because of the moduli, something about the modulus?
Yeah, I mean, so this connected component property. So these guys live in the same connected component of the moduli of the k lambda bar points of the moduli space. So they're conjugate. They're in the same GLR k lambda bar orbit. Sorry. Hopefully that helps clear up. Yes.
So the point over here showing that sigma goes to p sigma is well defined, right?
Sigma goes to p sigma. Yeah. So a priori these p sigmas are not well defined, only up to some scalars. But
Could you repeat how you get that?
so it's just right. So if we look at this subgroup of SLR, this one will map isomorphically onto its image in PGLR. So this is sort of like a finite atoll cover, if you like, and then we can lift after ensuring that all the p sigma bars live in this. So this gives us arithmeticity results. So if you buy the relative Montan-Maser conjecture, now you also buy Simpson's conjecture. Okay, so great. Let me see. I'm doing on time, so I have about 12 minutes. So I think that's enough to say some words about the Margulis superrigidity story. So sort of maybe another source of rigid representations, if you like. I don't think I'll be able to say very much, but hopefully something reasonably satisfactory. So I'll sort of talk about this story in a special case, so of this AGN that I mentioned earlier. So let me just say briefly how this comes about. So we first need to define the Siegel upper half space. This is these set of matrices, complex matrices with properly symmetric and positive definite imaginary part, and then some appropriate discrete subgroup of homomorphisms of this space, the quotient bar. So just the higher dimensional analog of modular curves. We call this gamma GN for the kernel of that sort of congruent subgroup of SPUG. And then we get action of this gamma n on the Siegel upper half space. So this action is topologically very nice. So that in such a way that the topological fundamental group recovers the this congruent subgroup we picked out. And moreover, this quotient smooth variety. Yeah. So there's some, okay, we need to make some, and at least 3 will make this work out rather than being just like a stack, which is a fine moduli space. For principally polarized abelian varieties, plus level n structure. So this level n structure is sort of essentially picking some symplectic basis for the n torsion, and this is what's killing off automorphisms and allowing this to be a good moduli space. But nice example of something that could have appeared as our x before, with a very explicit fundamental group. Now let me say, some examples of local systems that you might cook up on this moduli space. So first of all, while we have a fundamental group, let's just find a representation. Well, there's kind of a tautological thing where this is already sitting inside GL2G. See? So there's a local system on EGN. And another sort of more sophisticated thing you might do is the cohomology of the universal family of abelian varieties. So the universal variety over the moduli space. So two concrete examples, and it turns out that these are actually the same example, although I won't really explain this, but it's true. Not terribly deep. But what is a deep fact is the following theorem of Margulis, which gives us really strong information, essentially complete information about all local systems in this space. So for any representation of this gamma, actually this H1 will vanish. This is one version of these so-called super rigidity theorems of Margulis, which are very deep and I guess are another example of these theorems which require highly non-algebraic techniques, in this case difficult ergodic techniques, if I understand correctly.
Your G assumption.
My G assumption, yes, sorry, yes, again, I'm forgetting my G assumption. Thank you. G is at least 2. So, yes, so this is, maybe I'll write this out so that, because I've been sloppy about this assumption. So this theorem, actually what Margulis proves is a far more general theorem about applies more generally to irreducible lattices in Lie groups, so satisfying some density condition. And let me say this correctly. So connected semisimple, Lie groups with rank at least 2. So I guess these should be real Lie groups. So as real Lie groups, they have rank at least 2. So it would just be the dimension of a maximal torus, and this is sort of crucial assumption, it fails, and if this assumption is not there, and that's where this G, at least 2 assumption throughout is coming from. So really, this Margulis result is far more general and far more general. And I think, if I understand what Sasha was telling me correctly, is that this special case over here is actually a consequence of earlier work on the congruent subgroup problem for SP2G.
Can you say how exactly this lattice setting shows up here?
Yes, so our lattice is this gamma gn, which is a subgroup of SP2G and that's a lattice in the Lie group SP2G. That's sort of where this lattice is. Yeah, so this Margulis has this whole book, discrete subgroups of semi-simple Lie groups, many very powerful results along these lines.
Can I ask you a question?
Yes.
So how is this theorem related to something called like a BGT, Fording's chart has a book, which is about what is model space of computing queries. There's BGT and also some vanishing theorem here. And is this
I don't know. I'm not familiar with this book. It may well, but I don't know.
it's all about like it's also about like a representation of the
Yeah, I mean, if it has to do with local systems on this moduli space, I assume definitely things related to this more super rigidity are coming up, but I don't know the specifics. So I guess let me just state some corollary of this. So any let's say C local system, AGN is not just rigid but cohomological. So these 2 local systems, which are secretly the same local system, give us another example of rigid local systems. And yeah, so it's immediate from this cohomological formulation of cohomological rigidity. And I didn't say why this would in turn imply rigidity, but well, it's obvious from these moduli space definitions of rigidity. Yeah, maybe I'll just say one more thing. I think I have 1 more minute, so another result. So I'll say another corollary, maybe of like a different version of superrigidity that Margulis proves, is that actually any like this is a character of this gamma gn times some algebraic representation. So some restriction of algebraic representation SP, so SP2G, the GLR. So in this sense, this Margulis superrigidity result, or one of its variants, can be used to completely describe the representation theory, or more or less completely describe the representation theory of this gamma gn. And in particular,
One-dimensional representation.
yes, yeah, a one-dimensional representation.
There could also be like little things factoring for finding motion.
Right. Yeah.
It'll be literally tricky, just replace gamma G
Yeah. So, okay, yes, thank you. So so we get characters, but yeah. Right. Okay. So is a restriction of some algebraic representation, so SP2G, GLR, up to a finite quotient, up to finite quotients. But yeah, that's a correct statement here, and yeah, this can be used to give some sort of complete description of these local systems on these AGNs, and in particular, all of them will come from geometry. So these algebraic ones will all, these algebraic ones are all going to be generated by this tautological example, which is faithful, and then the finite index ones. So we already saw how these finite image representations are sort of not as interesting from the geometric perspective. It's coming from finite étale quotients. Yeah, so I guess that's probably a good place to stop. Are there any further questions? Yeah.
So is it correct that for groups where microbasis theorem applies, you get exactly the same kind of theorem for a family homogeneity for localism species associated?
Yes.
Just the same.
Yes, it works just the same. So I just stated it in this specific case. Yeah, easier to not introduce the documentation, but yes, just the same. Yes.
It's maybe a bit further afield, but wonder if this result has applications to a concrete of geometry moduli space, right?
Geometry of the moduli. So, yeah, I guess I would have to, I don't know any specific examples off the top of my head. But definitely this sort of result is important if you're interested in studying the local systems on this moduli space. I don't have specific examples of how it applies to the geometry. Yes.
So I just have a question of this rigid local system. So suppose I have a elliptic surface, or just over P1, and I remove a singular fibrous, and I look at the R1 high-local star, and I get two local systems or complementary points on P1. So is that rigid local system?
I don't know specific example. Maybe somebody in the audience does.
I think only if there's only 3 singular fibers.
Oh, it's sort of related to what you talked about in the first lecture, like the solution of a saturation equation, or is it related?
It's a little related. So if the discriminant locus is kind of a generic to the points in Q1, then it gives you one of these algebraics. But and those are completely classified. So those there are examples with 4, 5, and 6 points, I guess.
So being a rigid local system, is this equivalent to like being finite ordered under the Taiwan action?
No. It's much stronger.
It's much
The
stronger.
class of finite orbits it's a strict generalization of class of orbits.
So you're saying any local system over 3 points away from P1 is always rigid.
Rank 2 locus. Rank 2
Rank
is
2.